Hi everyone. So this talk will be about the development of category theory in homotopy type theory. As the title suggests, the Rezk completion, and it has to do something with univalent categories. Often when one considers categories in homotopy type theory, and one wants these categories to satisfy certain coherence condition, which is called univalence. Now, this is something that is really dependent on the construction or the definition of a category. And so certain classical constructions that we know fail to produce univalent categories. And so in this talk, we are concerned with one such construction. And then what we want to do is to actually produce this into a univalent, to actually get a univalent construction instead. And so to do this, we consider the free univalent completion. We are more precisely, we are interested in actually constructing a univalent toposes. First some introduction, some preliminaries, and some motivation for this, and then we will see how we are going to do this. So recall, so a category, it's univalent if the canonical map between the identity type and the type of isomorphisms is an equivalence for any two objects in your category. And there are a couple of reasons why one might be interested in. So perhaps the first one might argue, well, do we have examples? And the univalence axiom implies a lot of examples, like category of sets and, many categories built out of sets like modules or something. I would also, if one considers something like the simplicial set model of Hot, then the notion of univalence corresponds with the completeness condition for the Siegel spaces. Other reasons why one might be interested in univalent categories are that if one works between univalent categories, then certain notions which are classically unique up to isomorphism actually become unique up to identity. And also that equivalences between univalent categories are actually isomorphisms or even identities. And so in particular, like structure transposes along equivalences, and this requires, no proof at all, because you can just apply path induction. And so even though a lot of categories arising in practice are univalent, one exception to this is the so-called tripos construction. And so triposes were already mentioned yesterday as well. And so a tripos, can you point with this? Okay, great. So a tripos, it is like depicted on the left side of the picture, is a second order hyperdoctrine. So if you start with a category, then if you want, ideally, you want to be able to actually have some kind of calculus or some kind of internal logic for these categories. I mean, there are many reasons why one wants this. And so a tripos, one way to depict a tripos is by saying that you have a category which lives over it, and where each of the fibers then represents the formulas. And so this is an external way of adding a logic to the object. And now this is already great, but often you want actually the logic to be internalized. And this is what the triples to topos construction formalizes, or at least this is one intuition for this. So, and well, one way to construct this is by taking partial equivalence relations, where the where the notion of value of these relations is determined by the formulas. Now, if one, of course, one can just implement the triples-to-topos construction in univalent foundations. It's not an issue. However, already for actually like the trivial example, this does not produce a univalent category. So if you just start with your base category, by which I mean this guy, just to be set, and then you take the trivial triples, by which I mean, yeah, you say that, well, you only have like a contractible type of formulas, and so you just take like let's say the trivial Hating algebra. Well, then the consequent tuples that you get, well, this is just the category whose objects are sets, but whose each of the Hom sets are trivial or just a unit type, and so this is definitely not univalent because the identities in this category are by the univalence. By the univalence axiom, just the isomorphisms between sets, but well, in this category, anything is isomorphic. So, yeah. So even if we assume univalence everywhere, this construction breaks univalence just because we change the morphisms. Now, so one way to fix this is to consider the Rezk completion, which is a universal solution of making a category into a univalent one. So given a category and the Rezk completion, it should be a completion in a way. So it will be a univalent category denoted RC, and then a functor into it. Well, it should be, first of all, an embedding, so it's fully faithful, and it's also essentially surjective on objects. And by essentially surjective, this means that for every object in the codomain, there merely exists an object in the domain. And so it's really the fibers here. It's not necessarily inhabited, but only merely inhabited. And so I observe this is not an actual strict equivalence, so you can't necessarily find an inverse for this. And there are, in general, two ways to give an implementation of the Rezk completion. One through higher inductive types, which might or might not exist in your base type theory, or by taking the image factorization of the Yoneda embedding. So in this sense, you already need to keep track of universe levels. So you can only have it actually for small categories. And well, I say this is a completion, so it should have a suitable universal property, and this if you have the Rezk completion, so just a weak equivalence into a univalent category, and then you can show that for any univalent category, like any functor into this factors uniquely through it. Or at least this is the one categorical property of it. So you also have something about the natural transformations. So this more precisely, you get that precomposing with this guy gives you an equivalence of categories, or because these univalent, this is actually an identity even. And this guy here, this says, well, this you can phrase a little bit more generally, let's say, or too categorically. And what you get is that if the rest completion is given for every category, and this determines a left bias joint to the inclusion of the univalent categories into all categories. Okay, and yeah, so and I said in the beginning, we are interested in rest completion for Topoi, and so this is actually the result that we are after. So what we want to do is if you have the bi category of Topoi, and then if you restrict to the bi category of a Topoi whose underlying category is univalent, like the inclusion, does this have a left bi joint? Now to prove this, we take two steps. And so the first step is that we just generalize from the bi category of Topoi to more arbitrary bi categories over cat, and this is made precise through the language of displayed bi categories. And so this allows for a modular construction in the sense that just by setting up everything in this sense, it's a little bit independent actually of just of tuple structure. So then in that sense, what we do is we start with a bi category over cat, and then we can take the pullback along the embedding of the univalent categories to get a bi category over cat unif. Of course there is an embedding, and then the question is, does this have a left bi joint? And so with this, and so working with just with bi categories or displayed bi categories allows you to actually do everything step by step. So to have an incremental proof strategy for this. So for elementary Topoi, one characterization is that it has finite limits, exponentials, and a subobject classifier. And so you can build up this bi category of elementary Topoi just in these different steps, and then and what you want to do is actually construct then the rest completion or the induced bi joint for each of these different ingredients. Yeah, and so the first step was going from Topoi to bi categories, and then in the second step, what we do is we reduce the construction of the left bi joint in terms of weak equivalences, because we know how we concretely know what the left bi joint given by the rest completion is. So we want to work with that. And so this is the main lemma. Strictly speaking, this will almost be just an unfolding or just a reduction of the definition, but this will be set up in such a way that it also makes implementation or formalization nice, so that it really extracts I think the useful properties that you need. So mathematically there's nothing much going on, but it's the right setup. So to construct this left bi joint, what you want to do is you want to show something for all weak equivalences, or at least where the codomain is univalent. So in the first step, you want to say, okay, if you have some structure over a category, like some kind of limit, then the codomain also should have this. Then you want that this functor or this weak equivalence actually preserves the structure. And so here you define the action on the object, here you define the unit, and then here you define the universal, then you have to say something about the universal property, or actually the action on the functors, or the morphisms itself. And so, and this should say that if you have a natural isomorphism, then you can transport preservation properties. And so just using this lemma, we've given formalizations of proof that these kind of structures all commute well with rest completions. And so for that we have rest completion for these individual structures. And so finite limits, core limits, so we classifiers, and so on. And in particular, then we can conclude that the embedding of univalent topoi into topoi has a left bijoint. And there are a couple of other things one can do. So first of all, we have not yet done the case for locally Cartesian closed categories. Of course, if we have it for topoi, this should somehow follow. But also for the interpretation of like dependent types or the quantifiers, this is necessary. We can one can study the interaction between internal logic and the rest completions. We can but there's also the question like now we done like let's say abstract rest completions. Can we do it for more concrete stuff? So on. And so this is the conclusion, and I guess it's time.